What is speed? What is velocity? What is acceleration? Hello, today we're going to learn about the differences between speed, velocity, and acceleration. How exciting! Now, going back to our first question. What is speed? Speed is a scalar quantity with unit of distance over time. What is a scalar quantity? A scalar quantity is a value specified through magnitude but without any measurement of direction. Let's think of an example. If you look at a speedometer, you can see the numbers directing to how fast you're going. The speed. It shows how many kilometers can your car travel in an hour. Then how about velocity? Velocity is a vector quantity. What would be the difference between this and a scalar quantity? As mentioned before, scalar quantity won't have any mentioning of direction, but on vector quantities, they do have the direction. To make it look simpler, an example would be a car going 40 miles per hour north. Let's try comparing these two quantities with restrictions. If a sign tells you that you need to go below 40 kilometers per hour, it means you can go in any direction but under 40 kilometers. This is a scalar quantity. However, if the sign tells you that you need to go below 40 kilometers to the direction of left, it means you can only go under 40 kilometers to the left. With the direction, this is the vector quantity. This is a pipette drop experiment, an example for acceleration. As the distance off from the ground increases, the speed of the droplet falling to the ground increased. Acceleration is written as A equals speed or velocity over time. Here is an excellent video example. As the video is played frame by frame, we can see that the weight is going down farther in distance in the same period of time.
Freely falling objects and acceleration due to gravity. All objects, when dropped from a height, fall towards the earth. This happens due to the gravitational force exerted by the earth on the object. Suppose you drop simultaneously a small stone and a cotton ball of the same size from a height. Which of the two will reach the ground first? We see that the stone reaches the ground earlier than the cotton ball. So, we may falsely conclude that the heavier objects fall faster than the lighter ones. That is, the acceleration produced in heavier objects is more than in lighter objects. Galileo showed that all bodies, whether light or heavy, fall at the same speed towards the earth. Galileo explained that the lighter bodies fall at a slower rate due to the resistance of the air. Later, Robert Boyle proved this experimentally. He placed a coin and a feather in a long glass tube and evacuated it with the help of a vacuum pump. Robert Boyle observed that when the tube was inverted, both the coin and the feather reached the bottom of the tube at the same time. Thus, he concluded that the acceleration produced in all the freely falling bodies is the same and does not depend upon the mass of the falling body.
Did you know that physics is about how things move and why things move? It was Isaac Newton who discovered the 3 laws of motion. He was a scientist who lived from 1642 to 1727. Let's first learn about the first law of motion. It is also called the law of inertia. It states objects will remain at rest or in uniform motion in a straight line unless acted upon by an external unbalanced force. To understand Newton's first law completely, we need to learn about inertia first. See, this is a very large sofa. What's special about it? It's stable. It is not moving. Now go ahead and try to move it. Oh, you can't. It's not willing to move. You can't move it as it is very large. Now try to move this small stone. Good. You can move it a little bit, but you had to put in a lot of effort. It was also like it didn't want to move from its original position. Even the smaller things don't want to change their positions. They don't want to move. Even a small stone takes some effort to move. This is the first rule of physics. Things like to stay where they are. No object in this universe would start moving unless some external effort is put on it. It's like all things in the world are lazy. Now the question is, if things are lazy and they don't want to move, then how does the movement happen? The answer is that there are so many things in the universe which push and pull other things and force them to shift their positions, like you force the small stone to move. But as we said earlier that things are lazy, they would try and stop their movement as soon as the effort was removed. Well, you'll be wrong if you think like that. You'd find it very strange to accept that when a small stone was still, it wanted to stay still. But once you'd put it in motion after putting some effort, it would like to keep on moving. In reality, it would keep on moving forever and ever. But somehow it stops. But it stops not because it wants to stop. It stops moving because things in its path force it to stop. It may be due to air, or if it bumps into a tree or rough surface on the ground. But suppose there were no tree in its way, or there was no roughness on the surface, and also imagine that it does not have poles or trees in its way. The stone would never stop. It would keep on moving. It happens in outer space, where there's no air or roughness. If you kick a small stone, it'd keep on moving and would never stop. So how can we say that things are lazy? See, the small stone wanted to move forever, but it was stopped by the resistance of air, trees, or roughness of surface. It's like you moving on a slippery road. You'd keep on moving unless there was some effort put in to stop you. The same is true with the small stone in outer space. It would keep moving, as nothing came in its way. It also doesn't want to stop as it is too lazy to do that. So now we can change the first rule of physics. Things want to stay in the position they are, to things want to keep doing what they are already doing. If things are at rest, they want to stay at rest. And if things are moving, they want to keep moving. In other words, things are lazy. So there's a lot of laziness in the universe. Physicists have a special name for this laziness. It is known as inertia. So now you understand Newton's first law of motion. Can you write it? Well, you are very much right. Now let's move on to Newton's second law. As we know from the first law that to overcome the inertia of an object, we have to apply unbalanced force. Newton's second law talks about how fast an object would move. Well, it states acceleration of an object depends on the mass of the object and the amount of force applied. In mathematical terms, Newton's second law states that force is the product of mass and acceleration. To cause an object to accelerate or speed up, a force must be applied. The more force you apply, the quicker you accelerate. Look at these two swings. If you apply the same force on both swings, check whose goes faster. Let's first push the little kid. See? It goes very high. Now push this fat man with the same force. See, it does not go far, because it has more mass than the little kid. So the more mass there is, the force required to push the object is also greater. Let's look at the mathematical formula of the second law again. It's the product of mass and acceleration. We've already learned that if there's more mass in an object, to move it, we need more force. Now let's see this kid sitting in the swing. If we apply little force, then it goes a small distance. Now if we apply a lot more force, it goes very high. So to get more acceleration, we need to apply higher force. So now you can understand the relation among force, mass, and acceleration. Until now, we've only learned the first and second laws of motion. Oh, you're riding a bicycle. Have you ever wondered why a bicycle moves forward? Well, it moves according to Newton's third law, which says that for every action, there is an equal and opposite reaction. To understand this, see what happens when you drop a tennis ball. As the tennis ball hits the floor, it causes a downward force on the floor. This is the action. The floor reacts by pushing on the ball with the same force, but in the opposite direction. Action, reaction. Together, the floor and the ball form what's called the action-reaction pair. So now how it applies to your bicycle. When you push the pedal, the parts of the tire which touch the ground push it backwards. The ground also pushes the tires forward with the same force. So the parts of tires and earth form a pair of action and reaction. So what happens to the earth when your tires are applying force to push it backwards? Huh? Oh, nothing happens to it, since the earth is very big as compared to your bicycle. The force applied by your tires does not move it backwards, but force applied by the earth pushes your bicycle forward. So now you understand Newton's third law. Yep, the tennis ball is the right example. The ball and the floor are creating a pair of action and reaction.
Force of friction. Why do things slow down? Watch what's happening here. Why did the ball stop? Why did the bicycle slow down and stop? Moving things often slow down by themselves. Let us analyze the visuals shown here. The ball and the bicycle came to rest as the force or the push responsible for the respective motion was no longer acting on them. This shows that things slow down because a force is acting on them. This force always opposes the motion and is described as the force of friction. Force of friction can be defined as the opposing force which is called into play when a body actually moves or tends to move over the surface of another body. Let's perform an activity to understand what friction is. Place a wooden block with a hook on a table. Gently pull the block with the help of a spring balance. What do you observe? The block does not move even though the pointer of the spring balance moves. This shows that there is a force opposing the motion of the block. Now, gradually increase the force exerted on the block. At a certain stage, the block starts moving. That is, there is a limit to the amount of friction. This maximum force of friction is called limiting friction. The reading of the spring balance gives the numerical value of the limiting friction.